Welcome to today's hopefully quick lecture on how to use an orbital diagram to write the electron configuration of an atom in its ground state. So hopefully, like I said, this lecture will be much quicker than the title makes it sound. So what is an electron orbital diagram? That's just this right here. This shows the energy as energy increases, as the energy of the electrons increase. This is where the electrons fall, which orbitals they tend to fall in. So we're going to use this as a tool to help us successfully write the correct electron configurations of most elements. There are a few exceptions, however, in this class we will not be too terribly concerned about these exceptions. So here we go. Let's get started. So first step to use an orbital diagram is to start off by find the total number of electrons. E minus just stands for electrons in most cases, and this is going to be one of them. Find the total number of electrons in your atom, and this is just the atom that we're going to represent. My example problem down here is vanadium, which is right here on our periodic table. Vanadium, atomic number 23. Atomic number 23 means that when it's neutral, it's going to have 23 protons and also 23 electrons. So vanadium, we're going to, with the number 1, note that this has 23 electrons. Perfect. Once we've found the total number of electrons in our atom, we're going to go to this chart to start to fill it in. Now, here is process that we're going to use to fill in the chart. The arrow right here indicates low energy to high energy. As we've said in class before, Mother Nature is very lazy, so she's not going to fill in these higher energy orbitals unless she absolutely has to. So she's going to fill them in from bottom to top. So we too are going to fill in the chart from bottom to top. With only 2 electrons per line. Now, each of these lines represents a shape within the orbital. The 1s orbital, as we recall, s orbitals can only hold 2 electrons, and those are our spherical shaped orbital. So this right here, that can only hold 2 electrons. Next is our next 2s, which is slightly larger. This line right here in our XYZ plane represents one of our dumbbells. Then the second one represents our dumbbell on the other plane. And then our third represents the dumbbell on our third plane. As we continue, so we see that this is represented by that, 2, and then 3. As we can see, each of these lines represents one of our shapes that are inside of the orbital. Our p orbital can hold up to 6 electrons because we have 3 different shapes for it. Our d orbitals can hold up to 10 electrons because we have 5 different shapes, and then our f orbitals way up here can hold up to 14 because of our 7 different shapes that we have. I'm not going to draw those for the sake of time or space, but just know that each of these lines represents one of the shapes of our quantum orbitals. Now, in order to do this, we're going to start at the bottom and fill in our 23 electrons. So first 2 we're going to draw are in our s orbital. So there's 1, 2. Now we have 21 left to place. So the next one moving up is our 2s orbital. So we're going to put both of the electrons in here. That one's happy now. Now we have to keep going because now we have 19 electrons left. So we're going to continue to fill these up so that they've got 2 electrons. Each of these ticks just represents 1 electron. So now we're up to 10 electrons. We've got 9 more. So we've got to fill up our s. Next is our p. And then next is our next 4s. And then lastly is our d orbital. We only have to put 3 because we are up to 20, and then we've got 1, 2, 3 left. So we're going to do our 1, 2, and 3. Perfect. Now that this is all filled out appropriately, we're going to move on to step 3. In order to write the electron configuration, all we have to do is write down in order all of the orbitals that we put electrons in, and note the amount of electrons per orbital with an exponent. Okay, so what does that look like? For vanadium right here, here's our orbital diagram. We have 1, 2, 3, 4, 5, 6, 7 different orbitals filled in. So in order from bottom to top, we're going to say that we filled our 1s orbital. So we have 1s, and our exponent says that we've got 2 electrons in that orbital. Next, we've got our 2s orbital, and then we've got 2 in there. Now we've got our 2p orbital, which has 6, our 3s orbital, which has 2, 3p, 6, 4s, 2, and now our 3d, that one is not full, that one just has 3d, 3 electrons in it. And that's our electron configuration for vanadium. Now again, all that this tells us is how many electrons are in each of these shapes. So each letter represents a shape, and that exponent up here tells us how many total electrons we have. If we want to check our work, we can take a peek and see 2, 4, 10, plus 2 is 12, plus 6 is 18, 19, 20, 21, 22, 23. So as long as we add up the exponents and they match what we're looking for, which is our atomic number, then we've done it correctly. Hopefully this isn't a vast oversimplification of what we need to do, but in essence, as long as we're able to use this tool to write our electron configurations, then we will be successful. Hopefully this helps. Please feel free to reach out if we have any further issues. Enjoy.